Last couple of deadlines for the quarter. We have our last assignment due tomorrow. We'll have a review possibly starting tomorrow, possibly starting on Thursday. We will have the ability to vote by the end of class and or tomorrow morning into how we'd like to best utilize tomorrow's class. We could either have a work day on the project, and I'm happy to walk around and help you get started, help you debug, get unstuck. Or we could start a 2-day review for the final. That is Tuesday at 8. Then we have our LL parsing project that's due Friday. And that's everything for the class. Is it like 2 hours time? It is a 2-hour time for the final. And then I'm giving you the option to take it on Friday or on Tuesday. So you can take it on Friday during our normal class period, and that will leak over into my office hours. Depending on, it's designed to be 1 hour. So it should feel like a normal exam. But because if you're here during the final slot, you get 2 hours, but also get 2 hours if you're here taking it on Friday. And I leave that to you to decide what works best with your schedule, whether you would rather get it over with, take the extra time to study. We'll see. I think last time, I did this last time as well. What happened? I think I had something like 2 people taking it on Friday and the rest took it on the normal finals day, but I don't know, maybe this one will be different. Anyone considering taking it on Friday?
Depends.
We'll see. Couple people, maybe.
I feel like for the people in game development, it's like kind of the question.
That's probably true, considering they're also taking an exam. And then it would be back to back 2 hours, followed immediately by the house.
So it's like,
Yeah. Well, if you weren't here yesterday, I didn't get the lecture video up, so you probably haven't had a chance to look at it. It's going to be kind of like hopping into the middle of something you don't remotely understand. So let's summarize where we are with LR parsing before we finish it off. So LR parsing is a bottom-up parsing process. LL was top-down, where we started with the start non-terminal and tried to derive the string. LR parsing, we're starting with the string and deriving the start non-terminal, very much like CYK was. We looked at, let's actually just go quickly over the process again. Here was the example of the LR parse. So we find shifts and reduces. And both of these are elements that you need in Q0, the initial state. So a shift takes a terminal from the string and places it on the stack. And a reduce is going to take a right-hand side of a production when a right-hand side of the production is on the stack and replace it with a left-hand side, with the idea that we will eventually have just the start non-terminal on the stack. We unfortunately, though, had non-determinism at places. Whenever we could reduce, we could also shift. So we needed to determine whether it was worth shifting or reducing, which one of those is better. And we also needed to dig multiple characters down into the stack to know when we had a right-hand side on the stack. And neither of those were going to work with regards to what we've looked at in class. There's no way to make this linear if we're always diving down and arbitrarily deep into the stack, trying to figure out how much of a particular right-hand side do we have. So we introduced 2 new concepts, items and closure. And an item is just a right-hand side of a production with a marker in it, this dot. The dot signifies that everything in the right-hand side to the left of that marker is already on the stack. And everything to the right-hand side of that marker, we still need to see. We still need to shift that or reduce that into the stack in order to be able to have the rest of that right-hand side so that we could reduce that right-hand side into its left-hand side equivalent. And the last thing we did was define the concept of a closure and get an example of that, where a closure is every possible place that we could be, given that we're in a particular place in an item. So each item has a closure around it, or has a closure associated with it, that basically says if the item has a non-terminal to the right of it, then we need to know all of the ways that we could create that non-terminal and reduce that non-terminal before we could move forwards with this item. Someone left me a pen, I'm gonna even have to use my own. So the idea is that we really want to move this marker past this S. But to do this, we need to create an S on the stack. And we don't just put an S on the stack, we have to shift some characters and reduce them into an S. So how would we go about doing that? We need to be able to say, here are all of the ways that we could create an S. According to this grammar, there are two right-hand sides that reduce into an S. So we're going to start by saying if we're at this point, then we could also be at the left-hand side of every possible right-hand side of each of these productions. And if we see either of these, then we could reduce down into the S and then move forward in this item, having seen that S. So we need to acquire that S in some capacity when there are multiple ways to do it. When you do this process, you're going to loop. Whenever we add an item that is on the left-hand, the markers on the left-hand side of a non-terminal, we need to add the closure of that as well. So now there are multiple ways that we can generate this A. And we see that we add those to the closure as well. So basically what this closure is going to tell us, the example that I used last time, is that if we are somewhere in the string and there's a C that is the next character that is to come, and somewhere on our stack, we have the bottom of stack character, some symbols, and eventually we're going to shift this C onto the stack. We would shift the C, saying that we'll move past the C in the input. That goes onto the stack. As we do this, this marker would move to the right-hand side of this. It's now on the full right-hand side of this entire right-hand side. We can now reduce this C to an A by the rule embedded here. This C can become an A because we're trying to derive the start non-terminal. So we can replace right-hand sides with left-hand sides. So as we do this, we can replace this C with an A on the stack. And as we replace this C with an A, then this marker moves to the right-hand side of this A, since there's an A on the stack. So when we do that, we replace this A on the stack with the S. That is the S that we were looking for. And this allows us now to move forward here, which is the equivalent of moving forward here. So we'll be looking at the next closure of the next production. But this was the process by which we can reduce to move past that S, to move the marker one space to the right in this closure. Were there any thoughts on that? It seemed like that was a confusing aspect yesterday. Does going over it from scratch help? Do we feel a little bit better? Or we feel like this is still kind of confusing as to what this is and why we're doing it. Possibly about the same spot. That's what it looks like. Let's see if we can make this make sense. There's a big example coming. A very big example coming. The entire purpose of having these items in closure is that we need to know without digging into the stack when we have a right-hand side that's on the stack, knowing when we can do a reduce. When can we replace a right-hand side with a left-hand side when the marker is all the way on the right? So I'll give you some more here. So there's a marker to the left of S in this item. So this tells us that A is on the stack and SB is not yet on the stack. That's what that marker means. We know that a shift operation placed the A on the stack because that's the only way to put terminals on the stack is to shift them from the input string. And this is just everything we've already gone through. But to get S on the stack, we have to reduce an S production in some capacity. All the symbols on the right-hand side of an S arrow right-hand side have to be put on the stack in some capacity. So that's every option for the right-hand side of an S arrow production. So once we do that, then we can move past that. That's it. That's basically it. Here's the process algorithmically. So we weren't able to do this before, and now we have everything we need, except that we have mentioned that we need to look multiple positions down the stack in order to be able to do that. So we need some data structure that is going to allow us to tell us that. So how are we incorporating the concept of items in closure into the parsing process? And it turns out all we need to do is to build a DFA that will model every possible combination of items, closures, and the transitions at that point are either shifts or backwards transitions are reduces. And I'll show you how this works because it is wild and it is fun. So each state in the DFA is going to be a closure, basically. And we're going to associate with it a set of items that indicate which symbols could possibly be on the stack, as well as what we need to do or see in order to move that forward. And those are going to be the transitions out of that state. So as we parse through a string, we're going to be tracing through this DFA, moving forwards whenever we do shifts and backwards whenever we do reduces, with the goal of eventually reaching a final state. So we end up using one of the very first things we looked at in this class as a way of doing probably the most difficult thing that we've talked about in this class. So final state indicates that the full right-hand side is on top of the stack, and we can then reduce back where we came from to get rid of those symbols and replace them then with the left-hand side. I know that won't make a lot of sense just from the words, so let's see constructing a visual example, because that's where the magic happens. So we're going to take a look at this grammar, and we're going to build a DFA that models the LR parsing process. So the easiest way to do this is to add a new start symbol to the grammar S prime and just make a S prime arrow S production, which is a nothing burger of a production, but it's useful when we say that we've moved past that initial S, that we can now use that as a final state. So we'll see how that's useful here in a second, but then we're going to number the productions. So we have production 0 being that new production, and then we have 4 additional productions in our grammar. We're just going to number them. Start with a start state. Q0, we're going to call that state 0. From there, we're going to look at the closure of our zero right-hand side, 0 production. So closure of S prime arrow S just says here is everywhere that we could be at this point. So what we know is we are not yet past anywhere in the S. So we need to add that. We need to add this S could eventually be an ASB. It could eventually be an A. Looping from here, we need to add everything from this A so that if we could reduce to an A, we could reduce to an S so that we can move past the S. And this very first time that we do this tells us every possible last element of the stack that would lead to acceptance. Like for instance, imagine if there's some process before this, but eventually what's on top of the stack is an it's an ASB. So we see the A, the S, and the B. We could replace the ASB with an S, and then we could get rid of the S and accept. So that is one possibility for the end of this string. Another possibility for the end of this is if we have BAA on the stack, that can become an A, which can become an S, which can become just the bottom of the stack character, and that gets accepted. So this tells us every possible way that we could see a right-hand side. If this marker reaches the end in some capacity, that represents a legal state that can be reduced in some capacity all the way back to our S that we can then move past. So that's what that closure is telling us. And each one of these elements is telling us one such way of doing that. But somehow some of these are related, like this A, to get to this A, we could either come from here or here. So really we have this going back to there, this going back to there, this going back to here, and this going back to here as some process. Wherever it is that we find ourselves, there is a path back to an S if one of these four ends up on the stack. It's the only thing that's on the stack. So that's what we're looking for at this initial state in the DFA. If we find that, then we can move to a state that is a final accepting state that says we moved past that S prime. And if we move past that S prime, then we're done and can terminate. Questions on this? Calculating this closure, thinking about this closure, what it means? Stairs. Maybe a show of thumbs. How much sense? All over the map. Excellent. I think it'll make sense as we start going through it. If that's not the case, then I'll backtrack and go through it in more steps in more detail, I think is probably the best way to move forward. So we're going to associate this set, this closure set, with the initial state, and we end up with this data structure it is a DFA, but a state of a DFA also has a set that is attached to that vertex. And that set is the closure set that we just calculated. So we attach that to this vertex as a data structure. Vertex set pair. So we now need to loop. We're going to expand this state. And to expand it, each 5 elements associated with the state creates a transition out of it. So basically, if we see an S, or there's an S on top of the stack, that'll be a transition out to a new state. If we see this lowercase a, that'll be a transition out to another state. If we see this A, that is a transition out to another state, etc. So there are 5 outgoing transitions from Q0, one associated with each one of these characters being on top of the stack. Each time we do it, we're going to move the marker over the first character and create and calculate the new closure for that item. So closure of moving past and having something on the farthest right does nothing. So we create a new state and associate that item with it. Just that one item. For the second one, we're going to move the marker over the A, looking at A dot SB, and then we will calculate the closure of A dot SB. We will attach that to a state 2 and associate that closure with that state. And we continue this for the 3 remaining states. And we reach at least a midpoint of constructing this. So here's what that ends up looking like. Let's take a second and analyze this. So we have this item marker on the far left, transition out on that character. So if we have an S on the top of the stack, then we can transition from Q0 to Q1, which moves the marker from here to the right. For this, we made state 1, state 2. On that lowercase a, we move that the marker 1 place over. That is the first element that we see here. Then we look at the closure of everything from A dot SB, which is going to add, this is what we did for practice a slide ago. This adds 4 more items, all of the ways to create S, all of the ways to create A, since S can go directly to A. And if we can see any of these 4, then we would be able to now reduce eventually to the S that would allow us to move past this S. Then we do the same thing for the A, for the C, and the BAA. Just calculating the closure of moving the marker 1 space to the right in the item that was used to create that transition. So again, the state 4, just says we were going to move the marker one position to the right. That tells us the edge label for this. And it tells us the first element of the closure, and then we define the closure. When the dot is to the left of a non-terminal, we just add every right-hand side with the marker on the far left. These are all of the A arrow productions, and the dot is to the farthest left in all of the A arrow right-hand sides, saying that if we see some right-hand side that can be reduced to an A, then we could move past this A and see that. The reason we're doing all of this is because it tells us then we can do something like, let's say we see this C. When we see the C, that tells us, since this marker is on the right-hand side here, that we can reduce to an A. When we reduce to an A, we move past this, which is the equivalent of saying we can go backwards on this edge, back to here, move the marker past the A, since we reduced something to an A, which means we can go forward here, moving this past the A. Since this is the far right-hand side, this says we can reduce this to that. We go back here, look for a production to the left-hand side of an S. We can move this to the right of that, which says take that transition. And that transition tells us that now we are done. We've moved past the S prime and we can complete. So this, between these, what we're constructing here is the ability to parse this without digging down into the stack. The items enclosure that we have associated with this is actively doing that for us so that we don't need multi-pops. We don't need something more complicated than linear time. All of this is to keep this process at a linear time. We could always search down the stack, but there's no way to keep it linear if we do that. So continuing from here, this is just the expansion of Q0. We now need to loop for every state that we just made and expand that state. So we use a queue. We're going to add every state that we make to that queue to expand. Any state with a single element associated with it doesn't need to be expanded. So that creates 2 new states that need to be expanded, state 2 and state 4. So this had multiple elements, this had multiple elements, we need to expand both of those states, saying that if we can shift, if we see any of these additional characters, we need transitions defined for each of those. So expanding state 2 creates 5 new states, but some of those states have the exact same sets as existing states. If that is the case, then we can create an outgoing edge back to an existing state that has exactly that closure associated with it. And you continue this process of adding the new states, expanding those states, adding those states, expanding those states until the queue is empty. Once the queue is empty, we terminate and have the final DFA for the LR parsing process. And here it is. And this is just for a simple grammar. There were 4 productions in this grammar. You can imagine how fun this is if we're using a programming language's grammar. So let's actually look at this and try to do a parse. So what are we going to use? This is the process, but I want to ABCAB is what we're going to do. All right, so we start with just the bottom of stack character. We start in Q0. We need to shift the A onto the stack in order to be able to do anything. We can't possibly reduce starting with just the end. So first thing we're going to do is shift the A onto the stack. As we do this, we need to make some modifications or some changes to where we are in this DFA, given the character that we've seen. So we've seen an A, and this tells us we can move on an A from Q0 to Q2. We've seen the A that is associated with the first character of being able to accept this string. So we were in Q0, now we're in Q2, having seen this A. Having seen this A, are we on the right-hand side of anything here? We are not. So we are forced into a shift. There is no possibility for a reduce. We're forced into a shift. So we are going to shift the B onto the stack. From Q2, when we see a B, this tells us to take the B transition here. So we're in Q4. As we're now in Q4, we've moved past the B. And this tells us what we need to see to be able to do anything of interest from this point. We're not at the right-hand side of anything, so we can't reduce. We are forced to shift onto the stack. So we shift a C onto the stack. From here, if we see a C, we go to Q5. Since Q5 is final, that tells us that it's time to reduce. So we are now back in Q5. There's no outgoing transition. We're at the far right-hand side of something that tells us to reduce. So we're going to replace this C with an A and go backwards the direction that we came from. So we actually need to be storing this sequence as we go. So we want to go back to the state that we just came from when we reduce. And sometimes when we reduce, and it's going to be multiple characters off the stack in order to reduce, we need to look back that far. So we need to be storing this entire path as we go. All right, so this reduce tells us to go back from Q5 to Q4. But we've now moved past the A. So we're able to replace this with an A, which tells us we can move past this A and move to Q7. So I'm actually going to replace this Q4 with a Q7. We move back to Q4 and forward to Q7. This went through Q4. So we're now in Q7. We shift on the A. And that is the transition from Q7 to Q9. As we do that, we're ready for a reduce. We have the B capital A on the stack. That is the right-hand side. This tells us the three elements that are on the stack. The B capital A. So we can go back from right to left, undoing the transitions that we just did. So from Q to Q7 to Q4, that's that. And then the B takes us all the way back to Q2. Note that there were two possible B's here that are incoming to Q4. This is why we need to store this path, because there's ambiguity when we get there with regards to which incoming B transition did we originally take. And this Q2 to Q4 tells us which one it was. So we're going to go all the way back to Q2 as we replace the B capital A with its associated left-hand side, an A. And we end up back in Q2. And at this point, we can undo all of this work, because we ended up going back. So the only thing that is on the stack that is where we came from, we're storing a separate stack of this information of where we came from, is the Q0 for how we got to the Q2. So now we have that. So we're able to, now when we see this A, we just added that A. So we're going to move forward on this A to Q3. So I guess this is through Q2 to Q3. Once we're in Q3, that tells us we can reduce the A to an S. So we're going to do that. Actually, don't need this much space anymore. So we reduced the A to an S. We can move backwards to where we came from as we move past this and get to the S. So we're back in Q2 at this point. Then we can finally shift on the last B, since there's no, we're not on the left-hand side of anything anymore when we do that. What's on the stack here is an S. There's no, we can move past this S. And that takes us here. So this is again an arrow through Q2 to Q6. Once we're in Q6, we can shift on that B. Now the B is on the stack. We're in state Q8. As we do that, since we're in a final state, that tells us we can reduce. The ASB has to be on the stack in order to be in Q8, which it is. We don't have to dig to figure that out. The closure is telling us that that is what's on the stack in order to be there. So we can now reduce, go backwards, the B capital S, A, the B, the capital S, and the A all the way back to Q0. But that's going to be what's on the stack at this point. The Q0 to Q6 to Q8 is on the stack. With via Q2, Q0 to Q2 to Q6 to Q8. That's what would be on that stack. So that reduce takes us all the way back to Q0 and reduces the ASB all the way down into an S. And as we move backwards to here, we see that we can finally move past that S. That we've seen it. And that allows us to go to Q1 and remove the S. To move past that, that is the final state that says we can accept. How are we doing? That was a process. But we had a method of constructing this. And now there's a way to read exactly what we did. There was a path through this DFA using forwards and backwards transitions, storing where we came from. That meant that there was no reason that we ever needed to do something that was not linear in nature to verify that this string was in this grammar because of the closure that was associated with every one of these states. That's kind of messy, but it gets the job done. This would accept every string that is in that language and would reject every string that is not in that language in linear time. But these DFAs get very big very fast. So there's a bit of a space hit, but it's a one-time space hit to store this. If you can store this DFA, then at runtime, it's very fast. And the runtime for this is the compilation process, not the actual runtime of a program. But when you're compiling something, it can tell you very efficiently if it is syntactically correct. And as I mentioned at the beginning of this slide deck, there are more grammars that are LR than LL. So it is more likely you will be successful creating this than it is the LL parse table. But it's also worth noting that unless your grammar is LL1, that parse table is also a pretty large data structure. If you need 4 characters or 5 characters of a look ahead, how large is that table? We have a few minutes. Let's think about it. Fun math problem for people. Let's say we have an LL5 table, like our last example was, and the alphabet is just A and B and C. How many columns are in this LL table? Spend a few minutes to try to work this out. Yeah.
Can we go back to the definition of the, it's closure, like equals times
Yeah.
for like this section.
You want the closure example or the closure definition?
One slide up for it. Yes.
How many permutations do we have of length 5 without the end of string marker? Does that question make sense? This is all length 5 strings just using A, B, and C. We know we can have the end of string marker in a column, but we're not going to worry about that just yet. How many permutations do we have of these 3 characters up to 5 characters long?
243.
It should be 3 to the 5th, whatever that is. A or B or C in position 1, A or B or C in position 2, A or B or C in position 3, A or B or C in position 4, A or B or C in position 5, all independent of each other. Repetition allowed, order matters. A, B, A, B, A is distinct from B, A, B, A, A. So there are 3 to the 5th. Okay, how many are there where the end of string marker is in the last position? So we're going to say, who knows what's in the first 4 positions, but we know the end of string marker is in the 5th position. Three to the 4th of those, we always hold that last position constant, but there can be any permutation of characters in those first 4 positions. How about the end of string marker in the 4th position? How many do we have? What is the answer? Somebody who has a calculator. Normally I like to try to do these in my head. This is a little beyond me in the moment, at least this morning. Maybe some days.
321. Oh, wait, I have this.
Yeah.
364.
364? Oh. So there are 364 columns in this table. And of course, there have to be, then there are a number of cells equal to that times the number of non-terminals in the grammar. So we're looking at probably at least 1,000 cells for just an LL5 grammar with 3 characters in its alphabet. If we're looking at real programming languages, how many characters are we reasonably looking at? More than 3? How large of a look ahead are you going to need in order to determine the difference between different elements? Probably quite a few. So this table would get reasonably large, and you might want to use some techniques found in other classes to minimize its actual size in practice. But my point was that as disgusting as that LRDFA looks, it's actually not that bad when you think about how the LL table scales in size. It's just a little bit easier to grasp what the LL table is and does compared to the LR table, which when you first see it looks kind of like a mess. But yeah, there are real space requirements to everything here. All right, last little bit. All right. So I just on the slides have the exact example that I just went through, and here is how you would end up storing this. It turns out that the stack that stores the location that you are can be stored actually as a tuple on the stack. So where you go is stored on the stack as well. Why have two stacks when you could just combine them into one stack with a tuple? So we start at Q0. When we shift on the A, we go to 2. When we shift on the B, we go to 4. When we shift on the C, we go to 5. When we reduce to C5, we end up going, replace that with an A that goes to 7. Shift on the A going to 9. This entire thing reduces all the way down to an A, which takes us forward to 3. And now you can see how the state that we're in is stored on that stack. It is a lot easier in this case, rather than drawing it out, but there you have it. And we end up with the acceptance once we get to past that S, that state that moves past that S. That is the true final state that tells us that we can accept. But we can see when we shift and when we reduce, we know we keep track of our look ahead character, and we keep track of what state we are currently in, which is also embedded in the stack with the associated characters. So here is how LR parsing is done in practice. And of course, here is an explanation for that thrown on top of this. Again, for your reference as you care. But again, no homework on this, will not show up on the final because you haven't had any opportunity to work with this on a homework, and the class is only 10 weeks long. So this seems like a natural conclusion point of this is the state of the art for linear time parsing. This is what state-of-the-art compilers use to be fast. Since more grammars are LR than LL, most of the time they'll try LR because it's a big waste of time. If you try LL, it fails, and then you have to do LR anyway. So a lot of parsers are coded directly with LR. Long description. But I feel like I did that justice already. So each final state had only one item, a reduce production. So we never had any ambiguity of whether to shift or reduce. But it is possible to have a final state with multiple items. So in that case, we still have to choose between a shift and a reduce. We can still use look-aheads with this. So that was an LR1 grammar. And we will find that a grammar is not LR1 if there is any final state where you have the option to shift or reduce. So you may have to try to find an equivalent grammar that is LR1, or you may need to use look-aheads where you're now, instead of shifting on a single character, you're looking ahead multiple characters and deciding whether to shift or reduce based on that look ahead as to whether you shift on a single character and move your sliding window by 1. So yeah, look aheads can help when there's a lambda involved in the grammar. That actually makes things very challenging. And so you oftentimes have to default to CYK since look aheads won't always help you with that. But in the occasional grammar that is LR1 or the less occasional grammar that is LRK, then you get this nice linear time guarantee. This is the very last slide of the class. Any questions about anything? Yeah.
What's the DFA?
We're ready for the final, I think. How do we feel?
Other than this, good.
It would be nice if we could have some time to work with this and understand it a bit better. But I think this makes for a natural concluding point.
For next quarter, you should just jump right into it.
Have this be the very first thing on the first day.
They can
You
figure
hear
it
that
out.
future class, if anyone is watching the sequence of videos ahead of, does the professor always do this on the first day of class? Now you know who to blame. If you can pick out that voice,
Up and down on this, right?
you can pick out that voice from the rest of this, then you're good. All right, we'll call that good. I'm gonna go up and start some office hours for any assistance on homework, projects, clarifying any of these concepts if you're curious.
Do you want us to vote on tomorrow's class? thought you
I
said-
guess we could do that too before we leave.
Yeah.
Do we want to spend time tomorrow working on projects, kind of having some in-class time for working on project and getting some feedback associated with that? Or the other option is preparing for and having a longer review for the final.
Well,
So now that we know both options, project work time, 3 votes. Final prep time, more than 3 votes. We'll start there, and I think if we run dry of material for that, then we'll work on project stuff. Yeah. It should be. It's not. I'm gonna do that immediately as soon as I get back to my office.
I was thinking you guys have done a